Welcome everyone to this summary of Breakout Session 1 on offshore HVDC grid technology, presenting one of the puzzle pieces worked on in promotion for the development of offshore mesh DC grids. My name is Christina Brantl and I'm a research associate with RWTH Aachen University, and within promotion I was the lead on work package 2 on converters and topologies, and also involved in work package 3, 4, 11 and 12 at various levels of depth, and I was the project liaison with the TenneT working group on HVDC system aspects. So within this presentation, I'll give you an overview of the work on offshore HVDC grid technologies, and especially the key conclusions and messages from the different work packages working on these aspects. So let's first have a look at design considerations for offshore HVDC grid technology. When moving from the existing point-to-point to multi-terminal systems, we have to discuss the system design and normal operation conditions. So for example, taking into account the DC voltage levels, the DC configuration, the operational strategies, and of course, the main point is the interoperability of the different components and converters in the grid. The key aspect when moving towards larger DC systems is the handling of faults within those systems, as the fault impact will spread through the overall system when interconnecting those. So we have to discuss what are the requirements we pose on the system, for example, with regard to reliability and availability criteria, what are possible fault handling strategies for those new HVDC grids. And this involves a lot of new components. So for example, the protection IEDs, the breakers, the switchgear, but also possibly fault blocking converters, so different types of converters within the system. The main driver for offshore HVDC grid technology to develop is the integration of offshore wind farms. And as was already alluded to before, these offshore wind farms are expected to take over more functionalities in the future. So we have to define how these are used in the future. And the key element here is the new grid forming controls for offshore wind farms that also facilitate new functionalities such as black start. And of course, with the systems becoming larger and larger, what we also have to take into account is the interaction between the AC and DC systems, as they are closely interlinked. And one aspect here is the provision of auxiliary services between the systems. These have to be defined and ensured. And we also have to take into account the different frequency reserves, for example, of the connected asynchronous systems, but also the impact on the offshore wind farms. So this is a very broad field of design considerations for HVDC grid technology to develop. And this is quite challenging. So if we take a step back and look at the basis for AC grid development, or rather extension at the moment, there we have a given system design, for example, with regard to current and voltage ratings. We have the known passive behavior of the generators, and we have standardized components and operating sequences. If we now look at the DC systems, as was already discussed, we have different voltage levels and system levels and voltage ranges. We have different configurations leading to different behavior under fault and general different system setups. The overall system defined by the converters, and their capabilities depend on the converter type and the controls implemented. Overall, this is a very converter-dominated system, the offshore system. And then we don't have standardized operating sequences yet. One prime example is different fault clearing strategies being proposed and then leading again to different requirements on the offshore HVDC grid technology. So within these work packages, we had a look at all of these aspects to facilitate the development of multi-terminal HVDC systems. What we had a look at in specific is the development of HVDC GIS and the requirements on the HVDC GIS as a new component in the system. We had a close look at DC protection systems covering both the strategic side, so the strategies that could be used in future systems, the IEDs, but also, of course, new fault clearing equipment such as DC circuit breakers, which are needed for the multi-terminal system protection. Then, of course, the offshore wind farm controls were included, also taking into account the grid forming, for example, for facilitating the interconnection of diode rectifier systems where we don't have a controlled offshore HVDC converter. And then, of course, the overall system control and operation was taking into account studying auxiliary services or the interaction between the wind farms and the HVDC converters. All of this work was done by a broad range of partners and in a lot of work packages. So I'd like to present you here a main overview of the work packages that contributed to this breakout session report. Starting with the work package on HVDC gas insulated substation equipment, substation technology led by Uwe Richard from ABB Hitachi Power Grids, the work on HVDC circuit breaker performance characterization led by Dragan Jovcic from the University of Aberdeen, the work on HVDC grid protection systems led by Dirk van Hattem from KU Leuven, the work on wind turbine generator and converter interaction led by Nikolaos Kotoulilis from DTU, the work on grid topology and converters led by myself, and the work on harmonization towards standardization led by Paul Sorensen from DTU. So if you have any questions on lighter topics, please, you can always refer back to the different breakout session videos and presentations, and always contact us or read the corresponding reports and publications. So let's delve into the key messages, first on HVDC gas insulated substations. What are the challenges with regard to this? This is, of course, a new technology with quite different characteristics from HVAC GIS. This also implies that we need new partial discharge measurement approaches for the maintenance status, and for all these components, there are no specifications yet for the general requirements and the testing of the components. Moreover, as already stated before, SF6 is a potent greenhouse gas that is aimed to be minimized in future systems. So within this work, there was a successful long-term testing that you'll hear more about later, and we expect an equally long lifetime and minimum maintenance compared to HVAC GIS. Moreover, new partial discharge measurement approaches were developed and tested, which you can see here on the right, and also SF6 alternative gases were studied and verified. All of these work was then contributed to standardization in SIGRE and IEC bodies. When looking at HVDC circuit breakers, one of the key elements of protection of future HVDC systems, it's quite challenging because this is in general a new technology needed for the HVDC systems. They work quite differently as AC breakers. And then there's a broad range of proposed DC circuit breaker concepts. There's not yet an alignment on the functionalities, or there was no alignment on the functionalities before promotion. And there was a limited model availability to study the differences between the models and their performance under certain fault conditions. So within this work, there was the model development of 4 types of HVDC circuit breakers for in-depth studies, so of the different components within the breakers. And also there was a generic model for system level studies, so covering different types of studies that need to be done to really characterize and specify future HVDC circuit breaker performances. Also for 3 of the types, there were simplified models, but also real-time models that were then later on used in the demonstration work packages, which you'll hear on more later. And what was a very big part was the specification of the functionalities. So really specifying what is the key functionality of a DC circuit breaker, what are auxiliary functions that some designs may have and some may not, and also specifying the interfaces between the IEDs and the circuit breakers. For all of this, there was also a generic test circuit developed for the model validation of the different developed models. From this work, it was concluded that the focus of research or further work will be reducing the opening time, reducing the cost and the size of future HVDC circuit breakers. So with the DC circuit breaker being one element of the HVDC grid protection, now let's have a look at the work done with regards to the HVDC protection. Again, here, there's not one standardized DC fault clearing strategy, but there's a broad range of protection philosophies. And to evaluate the technical feasibility was not possible in the beginning. There was no set of required performance or key performance indicators to really compare the different proposed strategies and the implementation in different grid structures. Moreover, there was no MTDC relay available yet. And within this work, there was the successful development of a consistent set of requirements, analysis models, key performance indicators, and tools for protection analysis for further systems. And what you can see on the right-hand side of the slide is that there was an academic and industrial grade prototype ID developed, with the academic ID also being open source available. What was found out from the analysis was that several protection philosophies serve as a viable technical solution, and also that those different strategies could be used when different grids with different protection strategies are later on interconnected by, for example, using a DC circuit breaker as a grid splitting element between different protection zones within the grid. Moreover, to analyze not only the technical side, but also the cost side, there was the development of a risk-based cost-benefit analysis methodology for future HVDC protection systems. And what's the key conclusion here is that while DC grid protection is comparatively more expensive than AC grid protection, it is not blocking the development of multi-terminal DC systems. So the next step then is the HVDC network control, and here especially focus on wind turbine converter interaction. So as was stated before, the wind turbines and wind parks are expected to take over more functionalities in the coming decades, with them being increasingly integrated into the existing AC and DC networks. And grid farming controls here come as a key element to provide future services, or also to integrate diode rectifier units, which are a passive element, not relying on the HVDC offshore converter control capabilities. However, for these new functionalities, there were no validation and compliance evaluation procedures yet. So the work on this wind turbine and wind power plant studies concluded that wind turbine grid farming controllers can be used with relative ease for the diode rectifier integration, and that also black start operation can be carried out with partial or small modifications to existing wind turbine generator converters, so enabling future offshore wind parks to take over more functionalities. And also there were requirements and compliance evaluation procedures proposed and tested, and you can find the reports here on the right side, for example, with a lot of detailed studies of the different new developed control concepts under normal operation, under contingencies, under fault situations. So really ensuring that these new functionalities work fine for future HVDC grids, providing all the new services from the offshore wind farms. When then looking at the overall HVDC network control, this is also quite a challenge because there's a broad range of technologies and topologies in discussion. And of course, what we want to have in those systems is the interoperability of different converters types and also in general converters. There's an increase of requirements on the HVDC systems when they become larger, but there are no comprehensive specifications or grid codes yet for the offshore HVDC systems. So the starting point here was first to develop models and the analysis tools to really study larger HVDC grids, integrating the offshore wind farms and the interconnection with the AC systems for planning, operation, auxiliary services, and fault studies. And from this is what was concluded that the diode rectifier integration, the grid farming controls were already given from the previous work, that the diode rectifiers can be integrated into AC and DC connected offshore systems, and thereby also testing the interoperability of the different controls. So for example, voltage source converters with offshore grid forming and grid following wind parks, and seeing that also it's possible to have a smooth changeover from the different control modes. Moreover, there was further development of the integrated control, taking into account, for example, auxiliary services and the contingency in the AC system, but also checking the DC fault right through requirements on the offshore wind farms, ensuring a fast power flow recovery of the offshore wind farms within the DC grids. And then based on this very broad range of analysis of the system and for the different planning stages for the operation and the operation under faults, we then did an analysis of the HVDC grid codes and came up with a recommendation of steps towards future HVDC grid codes. I can't summarize all of them here, so you can have a look at the different deliverables published on this. But this ties quite nicely with the work on harmonization towards standardization done within the technical work packages. So challenging is that the HVDC grid technology is new and fastly developing. And there was major steps in the last 5 to 10 years. However, there's still limited experience with regard to HVDC grids. At the same time, there are increasing requirements on the offshore wind farms and the grids itself, and there are several standardization efforts going on in parallel. So this work really tried to contribute the work that was done within promotion to the different harmonization bodies, but also to ensure that there was that everybody was aware of the activities going on in the different bodies. So we had first a report on summary of all the activities within the field, which are quite a lot, and then contributed to the harmonization of HVDC systems, so the components, the controls, and the protection, to the harmonization of wind power plants, and especially with regard to the black start functionalities, grid forming controls, and the HVDC connected offshore wind farms. There was contributions to grid codes and compliance evaluation procedures. And all of these aspects covered the modeling, the system analysis, the specifications, and the testing of the different components and the systems. So overall, there's a fast increase of best practices and standardization for offshore HVDC grid technology that we've seen over the course of promotion in all the different bodies related to HVDC grid technology. So to conclude, what's the progress in offshore HVDC grid technology that we see? We think that the concepts, components, and knowledge are available to study and design offshore HVDC grids, and this covers the DC switchgear and breakers, the HVDC grid protection, and the control covering both the multi-terminal DC system operation and offshore wind power plants. Within promotion, we have contributed and initiated system design, functional specification, standardization, and grid codes for those future HVDC systems. And we think this is a very crucial aspect because the early coordination of system design and specification really facilitates the interconnection of future HVDC systems. When all parties know what the system can and will do, this is quite easy to, or this will ease the process of setting up the first multi-terminal HVDC systems. And these future HVDC systems can also then take over a variety of functions, so the hybrid assets covering both interconnection and offshore wind export, but also provide auxiliary services needed for the AC system. So now that we've presented the main conclusions from this breakout session, we'd be interested in what you think comes next. So which technical aspect do you see as the key next step to facilitate the development of offshore HVDC grids? And we singled out here the following 5 points: the performance improvement, cost reduction, and standardization of DC switchgear. Second point, ensuring interoperability by further developing standardization and grid codes. Or 3 different pilot projects. So the first option would be pilot project showcasing control and multi-vendor interoperability, pilot project showcasing DC grid protection, or a pilot project showcasing grid farming operation of offshore wind farm. So we'd be interested in what you think is the key next step, while of course all of these aspects are quite important.
And the poll is on. The votes are coming in. Still coming in, seems to be a difficult question.
Yeah, I think all of these options are quite important, but let's see.
Well, you got to pick and choose at one time, right?
Unfortunately. At least in this survey. In reality, I think most of them need to be tackled quite soon.
Okay, I think we have them all now. So I will share the results. And this is it.
I can't see the...
Oh, you can't see the poll?
No.
Let me quickly try to rectify that.
Yes, now I can.
Ah, excellent.
All right. So we have quite equally distributed between the first two. So ensuring interoperability, developing standards and grid codes is voted by 1/3, as I think one of the keywords, interoperability. And then half of the similar amount of people then stating that a pilot showcasing this control and multi-vendor interoperability would be one of the key next steps. So these tie in nicely together. And then, of course, we also have the performance improvement, cost reduction, and standardization of future components as one key step. Yeah, this ties in quite nicely. I think it also shows that it's not easy to decide what to tackle first, and that most of these efforts should be going on, start early and go on in parallel to really make the next step happen in offshore HVDC grid technology development. So thank you very much for your input here. And with this, I'd like to thank you for your attention. For further questions, of course, these were the key messages. If you want to have any more details, please don't hesitate to contact me, the other work package leaders, or the presenters of the breakout sessions. Thank you very much.
All right. Ian, I think the floor is yours. Ian, can you hear me? There we go.
Hello. Thank you, Jochen. So yeah, this presentation will summarise the output from breakout session number 2 from the build up to final conference. In this topic, we look at HVDC technology qualification, so moving away from design and offline simulation to the testing of actual equipment, be it primary plant or indeed controller hardware. So firstly, a brief introduction of myself. I'm Ian Cowan. I'm lead simulation engineer at the National HVDC Centre in the UK, which is part of SHE Transmission. And within the promotion project, I've been lead for work package 9, where we demonstrated DC grid protection. And it was my pleasure and privilege to chair this breakout session, looking at qualification, and indeed report back today the findings from all the demonstrator work packages. So in this 20 minutes that I've got, there's no way I can give true justice to the extent of the work done over the last 4.5 years. So I would encourage you to view the videos on YouTube put up as part of the breakout sessions and dig into the deliverables on the promotion website, along with the many conference and journal papers that have been produced. So during the live segment of the breakout session, we heard from each of the work package leaders for those demonstrators, as well as a TRL assessment based on promotion's impact on their respective technologies. So after each of the mini presentations on the day, we had a dedicated Q&A session where we had some interesting questions coming in. So today I'll briefly summarise each of those sessions and highlight a key question that came in for each. So first we come to the testing of the DC-GIS. It's worth highlighting here that the DC-GIS size advantage is something in the region of a 70 to 95% reduction for a DC switchyard. So when you consider the cost of offshore platforms, that's going to have quite a material impact on your project. So the testing was done as part of work package 15, and up to the present time, there's no international standards describing the requirements, applicable tests and test procedures for HVDC GIS that have so far been developed. So within promotion, the focus was given to the dielectric test requirements due to the different nature of the DC electric fields in comparison to the AC fields that we're used to dealing with. And additionally, due to the lack of operational experience on HVDC GIS, that's why there was a demand from utilities and regulators for the long-term testing to prove the dielectric performance of the prototype installation under actual service conditions. So you can see in the pictures the test setup that was used. The bus bar arrangement itself is not something you would expect to actually realise, but the DC test rig was there to include all the key components, so bus duct, disconnectors, earth switches, bushings, VTs, and everything that you expect to find, but not necessarily in the arrangement used. The nominal rating of the equipment was 320 kV. So the work on this started back in 2018 with initially getting the test set up configured, with the test starting in earnest in 2019. So for the tests, there was 6 blocks with a continual DC voltage. The voltage was increased by 20% to 400 kV for the duration of the testing, and each block was 60 days long. So every block included switching tests and lightning pulse tests, but each block had a different DC voltage by reversing the polarity or being with or without current, so it was up to 4,000 amps for some of the blocks. And the outcome of this long-term testing was that the DC GIS has a similar lifetime to that of its AC equivalent. So the key takeaways now was that the TRL level has increased for HVDC GIS. We've developed recommendations for specifying GIS, and importantly now we've got these test requirements, procedures and methods that have been developed that are ready for real onshore and offshore experience and can be used beyond the promotion project. Got the long-term test that's been carried out that have really helped to inform future works. and it could also improve models and develop the understanding of different potential failure modes. And Work Package 15 activities have been aligned and are actively contributing to ongoing pre-standardization of HVDC-JS, both in CGRE and the IEC. So an interesting question that came in directed at the GIS testing was, do the tests need to be repeated if the voltage and current increase? So in the first instance, it was highlighted that these are non-mandatory tests, so no is the hard answer. But if you consider an increase in current, as long as the temperature remains about the same, the test results are still valid, and you could double check that with a temporized test quite quickly. However, if you increase the voltage, because that would introduce a new geometry and design, you would need to repeat the long-term tests if you wanted to have confidence again. So now we move to the DC breakers, a key component in breaking fault current in a meshed grid. So the DC breakers were tested as part of the tasks of Work Packages 5 and 10. A lot of the work from promotion again was in developing the testing that would be able to subject the devices to realistic duties that would be experienced in the field, both in terms of the DC voltage stresses and the high current during fault conditions, including this rapid rate of change that would all need to be replicated in the testing. So they were able to design test circuits in an existing AC power lab, which means that there was no major cost in erecting a dedicated DC lab. The trick was using the low frequency of the generators at 16 2/3 Hertz. And with this, all the critical phases of interruption could be replicated. The most onerous test undertaken as part of the project had a transient overvoltage of 490 kV with a 20 kiloamp current that needed to be broken, and all that led to 10 megajoules of energy getting put into the test device. So all the testing was undertaken at Chemo Labs, and pictured you can see all the devices tested. There were 3 different technologies from 3 different suppliers. So from Mitsubishi Electric, there was a mechanical type DC breaker. From Hitachi ABB, we had the hybrid type, and from Cybrake, there was their BARC type breaker. Each of the devices were subject to different voltage levels and current depending on their design capabilities, but each passed their respective tests. So coming to the key takeaways from this work, the offline fault studies of HVDC multi-terminal systems were used to define stresses on circuit breakers that were required to be replicated in testing. With that input, a complete test environment for HVDC circuit breakers could be developed and is available for future tests, which can provide adequate stresses to fully test their suitability for projects. It was important to define standards for future breakers, so had experimental circuit breakers so they were free to take measurements to quantify stresses on the breaker subcomponents. And as part of this, the DC breakers are complicated with a lot of standard devices included, but subject to abnormal stresses. So includes vacuum circuit breakers and surge arresters. And as part of the work, we were able to create an inventory of non-standard stresses on these standard components. And all this input allowed for test requirements for fault current interruption to be agreed with industrial partners, giving a common platform and therefore even playing field for these tests. And just to repeat, the 3 technologies of industrial HVDC circuit breakers have been demonstrated, which also demonstrates the ability to replicate these fault stresses in the test environment. And this is the first time an independent verification of complete fault current interruption process has been done. And building towards standardization of technical specification, this has been supported with the work with the inputs from all this testing being directly input to IEC working groups and CGRE working groups. And similarly, the outcome of all this is the TRL level for DC breakers has increased. And the key thing here is to note that fault elimination is no longer a technical hurdle for HVDC grid development, as we can now be confident in these DC breakers. An interesting question directed at the breaker technology verification was, harking back to the use of models, what are the limits of these models? And you could alternatively view this question as, why are physical tests required? And the answer coming back highlighted that there's stochastic variables to consider, which field measurements can perform. And it also pointed out that models developed are mostly looking at the electrical parameters, but there's still a large mechanical aspect to consider, and that's where these physical tests really come into their own. So moving now to my work package, looking at HVDC network protection demonstration. There were sort of three main work streams within this. Within the first, procedures and guidelines that were developed that could be used to assess the performance of protection devices intended for use within a DC grid. These are applicable across any of the protection strategies or configurations used, and the full details are available in deliverable D9.2. The other two tasks led to public demonstrations of different strategies. So within the work hosted here at the National HVDC Centre, we showed the promotion IED and Mitsubishi Electric prototype devices in the loop with real-time simulation testing for partially and fully selective strategies. For some of the testing, we're also able to make use of the replica control and protection cubicles we have for the KNS Murray-Shetland system, which will be the first multi-terminal scheme in Europe. And as part of all this, we created a benchmark model in RTDS, the details of which can be found in D9.1, and the demos will be available online for you to rewatch on the promotion website later as well. Within the work led by Supergrid Institute at Lyon in France, the focus was more on the non-selective strategy. They developed prototype IEDs on Raspberry Pis and a grid controller that were used, again, hardware in the loop with real-time testing. Here they showed interoperability with the use of IEC 61850 to communicate between their devices. And also as part of this, they created the benchmark, but this time in Opal RT, the details of which can be found in D9.5. So across these two demonstrators, we've covered both half-bridge and full-bridge converters, each of the protection strategies that could be used, and made use of all the different circuit breaker models that Christina mentioned earlier. So regardless of which route we eventually go down, we can be confident that there's protection devices out there that will cope with it. So the key takeaways from us are that we demonstrated successful operation of fully, partially, and non-selective protection schemes on the most realistic test cases that we could come up with about installation on a real power system. And the main thing is the IEDs that we tested are expected to be sufficient for potential future HVDC grids. We evaluated interoperability of these protection devices, demonstrating that a multi-vendor protection system could be achievable, including the use of IEC 61850 in some cases. Created a prototype system supervisor for the non-selective protection scheme, and we developed real-time models for use in future benchmarking performance of other real IED devices that come along using hardware and loop testing. This included the integration of the DC protection systems and protection IDs from Work Package 4 and the breaker models from Work Package 6, as well as we've got our test procedures for assessment of the primary and backup protection operation. Now, an interesting question that came in aimed at the protection demonstrators was there an impact on the primary plant ratings for the inclusion of a DC breaker? So without doing extensive investigation, when you consider the use of the replica control and protection panels, the fact that we're able to integrate the physical IDs and breaker models without changing settings on the protection settings as set up for an existing scheme that didn't have DC protection and it worked, it suggests that there wouldn't be a significant impact on the primary plant, as none of the primary plant protection triggered during some of this testing. So now we come to DC grid and offshore wind farm control. This was done as part of Work Package 16. Again, this comes as a three-parter. Part 1 was a demonstration of controllability and interoperability. As part of this, a fully operational MMC test bench system was created at the premises of RWTH Aachen existing testing facilities. This allowed for power hardware and loop testing to be undertaken. A number of test cases were done utilising the testing capabilities of this test bench, and it was looking into the crucial interaction between different converter controls and conversion technologies and the protection system, as well as the interaction of the meshed HVDC offshore grids and the existing onshore system, with a particular emphasis on harmonics. The test cases covered different configurations of the multi-terminal setups, offshore wind, and the different AC support concepts. Part 2 was control hardware in the loop testing for offshore wind farms. So they demonstrated the operation of a diode rectifier unit connected to wind farm, and black start from offshore via direct AC connection, where they integrate the control hardware, wind turbine controllers, and commercial protection relays in a real-time simulation test bench. Lastly, part 3 was looking at stability assessment methods for offshore networks being developed and tested against the test bench. Since offshore collector grids are 100% converter-driven networks, there's no natural damping from synchronous machines. Therefore, it's crucial to investigate their stability during an early stage of the project. So in promotion, methods on how to assess stability in offshore collector grids were developed and demonstrated. A special emphasis was given to the characterization of the frequency-dependent impedance of HVDC and wind turbine converters. Using this measured frequency-dependent impedance, they could then measure stability in the grid with frequency domain analysis and time domain validation method. So coming to the key takeaways, the work here validated the earlier work from the technical work packages, demonstrated the control and protection of multi-terminal HVD grids, making use of this test bench, compromising downscaled converters. The outcomes matched very well the earlier offline results. They were able to demonstrate the operation between multi-terminal HVDC and wind power plants in grid following and forming control mode using the power hardware in the loop environment. This was the first, albeit scaled, physical demo of DC bypass breaker concept with a full bridge converter. We were able to verify grid forming wind turbine and power plant controllers using control hardware in the loop and develop compliance and evaluation procedures. This for high voltage AC, black start and island operation, and also the connection to shore via diode rectifier units. This was done with multiple academic wind turbine controllers implemented on physical hardware, as well as a manufacturer supplied wind turbine generator controller, which was tested at DNV-GL. The demonstration of converter black box model validation method for grid connected converters using controller hardware and loop harmonic impedance spectrum measurement. They verified the wind turbine converter using a commercial 1 megawatt wind turbine converter and the corresponding control replica. Verified the MMC converters using the lab scaled MMC and corresponding control. And overall, the method worked well, but it highlighted that models aren't always sufficient and you're better with the measurements from a real controller. The demos, again, are available on the promotion website, and all this work is contributing towards different working groups. Now, an interesting question directed at this work package was seeking confirmation about the ability to black start from wind, and the answer there is that the technical solution as demonstrated is there, but there's low experience, and this is especially hard to come by for black start. And the real challenge now is to have the business case in the markets there for the developers, as we heard earlier. Finally, a note on the technology readiness assessment. The TRL is important as it gives the gauge of the technology's maturity and therefore deployability. On this slide are the levels and a brief description of what this means. For assessing technologies and promotion, the definition of each TRL against the original NASA TRL scale was adapted to reflect the technology development for primary and secondary HVDC transmission assessment. So the scale takes you from 0, an initial idea, through to 9, where you finally have a commercial competitive product with operational experience. A full detailed analysis was undertaken for the different components right across promotion, and it's available on the promotion website. It's deliverable 12A. Coming finally to the analysis. So for each of the aspects demonstrated, we can see the TRL after the impact of promotion. So for DC breakers, it's been raised to 2.7. Again, it's important to remember this is across multiple manufacturers. For DC grid protection and control, the TRL is up at 6. And last, by no means least, TRL for HVDC GIS is all the way up at 8 now, the highest that can really get to without installation on a real system. The other thing to consider is that throughout the demonstrators, there's been interoperability between these different components, and that's been checked at a greater or lesser extent. And so the main takeaway for the TRL assessment and indeed the demonstrators is that thinking back to that mesh DC grid components conversation that Christina presented, there's no technical showstoppers for a multi-terminal HVDC grid. And with that, that's all from me. Thank you for your attention. If you have any questions, feel free to get in touch with me or any of the other work package leads. We do now have a brief poll of 4 questions where we hope you either agree or disagree. It'd be great to get your input on those. Thank you.
Yes, we have one poll coming up, and would just like to know the opinion of our audience. Our demonstrations show that all the key technologies for meshed offshore grids are sufficiently mature for real-world full-scale pilots. And we would just like to know whether you agree or disagree. And the votes are still coming in. All right, I think we got this. And these are our results.
That's a strong agreement. Good.
I think so too. I think you. Right. Yeah. Excellent. Well, then I think we should move on, and I think the next one on the floor will be Marc. Marc, it is.
Thank you, Jochen. Yes, thank you. Could you give me the presentation rights?
Yes, you already are, and I will hide the poll, and you should be good to go.
Thank you, Jochen. Good morning, everybody, also from my side. It's a pleasure for me to summarize the breakout session 3 on legal, regulatory, and economic aspects. My name is Marc Schmidt. I work for TenneT since 2009, and I'm heading the Department of Regulation Germany within the Regulatory Affairs Unit. As member of the promotion project, I lead the work package 7 on regulation and financing. Before I come to the content, I want to thank all the contributors of the work package and the breakout sessions. So we have Cecile from the University of Groningen, who is responsible for the work on the legal framework. We have Plet from Florence School of Regulation, who leads the work on the economic framework. We have Alexandra from Deutsche WindGuard, who leads the work on the financing framework. We have Lawrence from the University of Delft, who analyzed the offshore market design. We have Hannah from Carbon Trust, who contributed to work packages 7 and 12. Further, we have Jelle from TenneT as a member of work package 12. We have Carlo as a member of work package 7 and worked on the promotion project on behalf of TenneT. We have Santino from TenneT, who is involved in work package 7. And we have Kilian, who was the former lead of the work package 7 on behalf of TenneT and now works for Transnet BW. Again, many thanks to all of you for the work you've done and for the contribution in the breakout session. Content-wise, I will summarize the breakout session on regulation and financing, but also come to some parts of the deployment plan. Overall, I clustered that into 5 topics. First, the legal aspects and the question, how do we cooperate? Second is the topic of hybrid assets or small bidding zones. Third, how much does a meshed offshore grid cost? The fourth topic deals with the question of how to attract investments in a meshed offshore grid and how this can be financed. And last, but very interesting, the recommendations and the timing for an efficient rollout of the grid. We are confronted with a lot of questions on legal aspects. In general terms, how do we cooperate? But more specific, on what topics Should the coastal states or the European Union states cooperate? On which law is that based? Do we need additional agreements? And if so, which type of agreements do we need? In terms of timing, when do we need such an agreement? And why is long-term stability so important for mesh grid development? In general terms, one could ask, do we really need a common legal framework? And the answer could be no. No, because the coastal states can solve the problems as they come along. And no, because we can focus on short-term projects first. On the other hand, the answer could be yes. Yes, because the earlier a legal framework is created, the more benefits will be there. And yes, because for investors, a stable legal framework is key. In case there is no legal framework, it will hold back investors as they cannot trust the legal framework. And yes, because experience from the past shows that it takes time to develop a legal solution. And our conclusion is definitely yes, a legal solution should be there. And how should that look like? It's very important that the states around the North Sea all have a similar idea of why we are building a meshed offshore grid and on which values and principles it should be based. If the states differ about their opinion, this will lead to trouble when it comes to the construction of the grid. Our recommendation is that the legal basis of cooperation should be a North Sea agreement. The governance structure could be, for example, a high-level conference which takes place annually about big decisions. Some decisions are not so big, but very important, and others are very technical or economic. And the idea is to create a committee structure to treat these technical, economical, or spatial planning issues. When political questions arise, they can be solved in a high-level conference. On the organization of decision-making, one key question is, for example, do you need a qualified majority or a simple majority to make a decision about a topic? This type of issues need to be addressed. It needs to be addressed at the beginning, before the states come across. Obviously, the grid will be a natural monopoly. No real competition between the grid owners is there and makes no sense. The question is how the regulatory supervision can be created for an offshore grid. The best way to make sure we will have a cooperation of the national regulatory authorities. Last point here is on conflict resolution. If the parties and grid owners get into conflict, it is important to know how this could be solved. Almost every agreement has a part that says how conflicts should be solved. The second and most discussed topic in the breakout session is about the question if we should go for a regulatory solution with a hybrid asset regulation or a market-based approach on small bidding zones. As you can see on this slide, the connection of offshore wind farms is changing. The status quo on the left-hand side shows radial connections on the top and hub connections on the bottom, each to one country, here country A. What we see as a future development is a hub-to-hub or even a mesh situation where you don't have a link only with that country A, but also with another country such as country B or even with countries C and D. The current legal framework is not ready for this kind of connections. Interconnection rules are applicable, so in future 70% of capacity should be available to the market. Efficiency dispatch could require trade from high to low price zones. This would require subsidizing these transactions or curtailing wind without the physical need to do so. Or TSOs could just make the line capacity much higher in order to still comply with the 70% rule and evacuate the wind energy. Or TSOs decide not to construct the extra link, even though there are societal benefits to do so. And the question is, how can that be solved? Within the promotion project, we developed two solutions. First, the hybrid asset regulation, where we introduce a new category in the electricity regulation. Or the second one, small bidding zones, which divides the wind grid into different price zones that are defined by network congestions. Both solutions have advantages and disadvantages. A big advantage of hybrid asset regulation is that we do not need big changes towards national support schemes and interconnector rules. It's a relatively simple solution and comparable to the current model. On the other hand, small bidding zones lead to economically efficient investments and dispatch. And there is no need for an extra definition in the electricity regulation, which has just changed. Possibly, this leads also to a lower financial support to wind park owners. Before we come to our conclusion, I'm interested in your opinion. So, Jochen, could you please start the first survey? And I ask all of you to state, how would you solve the problem? The first option is, do nothing. Of course, because there could be no need to do so. The second option is a market-based solution with the small bidding zones. The third option is a regulatory solution with a hybrid asset regulation. And the fourth option is we should implement both, as both will take time to be implemented.
And the votes are coming in. Still getting votes. Leave it on for a few more seconds and all right, last chance and done. Let's look at the results.
Jochen, could you again share it with me, please? I have the same problem as in the breakout session and cannot see it.
Takes a moment to do the.
Yeah. We also saw in the breakout session that this is not an easy topic and creates a lot of questions, but you go for the same tendency as we have from the promotion project, because we highly recommend to implement both solutions, as both will take time to be implemented. So, yeah. We should introduce a new category of hybrid asset in the electricity regulation and further define that. Offshore price zones can be a solution which create optimal incentives for efficient dispatch. In this solution, there is no need for counter trading, and we have an optimal use of cross-border network capacity. And although in the presence of hydrogen storage or other types of consumption offshore, this solution will work. So, clear implementation of both solutions, as both will take time. Let's come to the third topic, which answers the question, how much a meshed offshore grid will cost.
Marc,
yeah?
1 second. I don't see your presentation. Can you make sure you're sharing it?
Yeah, sorry, that was interrupted here.
No worries,
Yeah.
That's what I'm here for.
Thank you. The answer to that question is, it depends. It depends on the concept, how you connect the wind farms. In the 4 illustrations below, we have 3 countries, A, B, and C, all coastal countries with wind productions. The illustrations differ by the ways of grid connections from wind to shore. First, to the upper left, we have the business as usual concept, which consists of radial point-to-point connections from wind to shore. Second is the national meshed concept, where constraints on point-to-point are relaxed, but wind farms may only be connected to the countries in whose exclusive economic zones the wind farms are located. The third is the European meshed grid concept. Here, constraints are further relaxed to allow wind connection to the closest onshore landing point. And last but not least, we have an island or hub concept with much larger hubs which evacuate power to shore. The costs were then estimated with a methodology which takes into account the different topologies itself, the main components, and the design of the topologies. What comes out is shown in this table, which gives an overview about CAPEX and OPEX. The slide is divided into 5-year periods, where the cumulative CAPEX and OPEX for these periods are shown. To the right, you see the total costs, and it can be seen that the hub concept has the overall lowest CAPEX, amounting to around 170 billion by 2050, given an installed capacity of around 200 gigawatts. For a fair comparison, of course, also the benefits need to be considered. The costs lead us to the fourth topic and the question how to attract investors and how to finance that. First of all, we see a higher need to coordinate national wind and grid planning. If this is done, the investment needs become transparent, and this provides clarity for investors on the pipeline of projects and the estimated investment volumes. That is highly connected to a mixed partial agreement between the countries, because this will lead to a higher coordination and binding commitment. Very important for investors is the regulatory framework, because that determines the regulatory income. Currently, we have this certainty on national levels, but not for a meshed offshore grid. That is why it's important to have long-term, stable and predictable regulatory framework. This brings clarity to investors about regulated income and their cost recovery. Elements like having no time lag in cost recognition and a clear allocation of liabilities are key to determine the investor's risk profile. Within promotion, different financing structures and options for ownership models were evaluated. We looked at the obvious one to have TSO structures and cooperations among the involved TSOs. Secondly, we looked at tenders of transmission assets to third parties, the British model. And the third option is even to have one builder for the meshed offshore grid. As already mentioned, remuneration of investments is key. In the short term, financial support by the European Union is highly recommended to eliminate risks for the investors and to bridge the financing gap. In the long term, a regulatory remuneration with a stable regulatory framework should be created to give the right incentives to invest. What do we conclude on financing? First of all, the legal and regulatory framework needs to be in place, and it needs to be adequate. Otherwise, we will not have success to develop a financial framework. The second is collaboration, coordination, and most important, a political commitment is needed. And third, the European Union should support in financial terms, but also in terms of coordination and in making the transition from national policies to common vision for the North Sea region. In the breakout session, we also discussed on cross-border cost allocation, which is another important element besides financing and tackles the question where the cost should be allocated. Finally, the deployment plan brings together technical, regulatory, and financial aspects. It develops a recommendation for the deployment of a meshed offshore grid. You will hear more about that later by John Moore. In breakout session 3, we looked at the rollout and the concrete stakeholder actions. As a development within the next 10 years, we see that there will be a standardization. The standardization we expect to be at 525 kV level and 2 gigawatt connection capacity. In addition, we will see hybrid assets and hopefully the first artificial islands with the hub concept. During this period, stakeholder actions are key because this is a starting point. We need a regulation on smaller bidding zones and hybrid assets as well as a North Sea Treaty. The period between 2030 and 2040 is seen as the acceleration period in the wind development. In this period, we need to scale up, expand artificial islands, and the meshing is an important topic. On the stakeholder side, with more meshing, we need solutions on the support schemes. The acceleration period is followed by the stabilization period between 2040 and 2050, which is marked by further expansion of meshing and increased interconnection capacity, which at the end hopefully enables a full market integration. In this period, we either need life extension investments for the first assets or clear guidelines for decommissioning. This slide now summarizes the roadmap of a meshed offshore grid. We divided it into different streams, and it shows the necessity and the actions over time. As you can see, to reach the target of having a meshed offshore grid by 2050, immediate action is required. Now I again need your action. After you heard the summary of the breakout session, what do you think is the most important topic to address with regard to realizing a meshed offshore grid? Is it a regulation and the market setup, meaning, for example, the discussion about hybrid assets and or small bidding zones? Is it number 2, the ownership of the grid? Is it number 3, the financing of the grid? Or is it number 4, the governance with a political commitment?
And the poll is running, and we're getting our votes in. Also seems a tricky question. Folks are still voting. All right. Give it a few more seconds. Last chance to vote. All right, and we're closing the poll. Give me a second to share that screen. And these are our results. Can you see them, Marc?
Yeah, I can see them. Thank you. I think that's a good handover to John with the deployment plan. And so thank you for your attention. Looks like a clear result on regulation and market setup, followed by the governance, the political commitment. John, do you want to take over?
Yeah, thank you, Marc. I allowed my video and stuff. I think I need to get presentation rights.
One second. You are the presenter now. Good to go.
Okay. Is that okay? It says paused. Okay. Good afternoon.
Just see a white screen right now.
Sorry?
I just see a white screen right now.
Why does it say paused? Okay, wait a second. Let me try a different way. Is that better? It says, I don't know why it's, oh, wait a second, let me just do it on the screen. Yeah?
Yes.
Oh, that's better?
Mm-hmm.
Okay. Good morning. Let me also introduce Olivier Antoine. Olivier, can you talk a little bit about yourself?
Okay, thank you, John. Hello, everyone. I'm Olivier Antoine, Senior Power System Expert with Tractable Impact. I would like to say that I'm very honored to present this with John today. And as already said, an amazing work has been performed in the project. And it was a great pleasure to have been part of this and to be able to share some key messages with you. My role in the project was to be a Tractable co-leader in the work package 12 on a specific task related to developing optimum wind scenarios and topology for the offshore grid. And I will now give the floor back to John.
Okay, I'm John Moore. I work in business development for TenneT. I've been leading, I have a corporate finance background rather than a power engineering background, but I've been leading work package 12 of the promotion project on behalf of TenneT, looking at trying to pull together the big picture of the project. So when I started this project, I started asking, what do you expect from a deployment plan? I received various answers. The first one is a story. This implies a logical flow of facts, but it also implies fiction. Indeed, what we're going to predict in the future gives direction, but this is one version of a possible truth. which may or may not happen. Like a story, we anticipate many twists and turns where alternative subplots may emerge. What we say should happen, but may not happen. However, a story does come to a conclusion, and we do believe that it is possible to reach the conclusion. It could be a roadmap. A roadmap has many routes. Each stakeholder may eventually choose or select his own route, whereby we do not all reach the destination in time if we actually reach the destination. However, it's now 2021, so we have TomTom or Google Maps, which can help us guide through the sort of complexity and hopefully avoid hazards. And the destination remains important. The last one we have is a rather more pragmatic list of tasks to be done, a list of recommendations where we try to identify who should lead those tasks, when they will be needed, and how they can be done. This is practical, pragmatic. It's maybe not as exciting, but it gives a kind of guideline to what must still be done, who should take responsibility, and who's involved. It looks to the future, and it's probably the closest to what we have tried, or what we have achieved. We have tried to identify who needs to ensure the task is completed, and who are the close by influencers, because in each task that we've defined, there are more people, there are many stakeholders that would like to be participant and need to be listened to, and there are many people who need to get this done. So to create the deployment plan, what we have is based on a huge amount of analysis. It's not just the analysis outside and the work done in the technical packages. It's also analysis which we've done in our own work package. But the idea is to take this analysis and look into the future. We've generated specific solutions, but the tools developed can be also used to develop many other scenarios at a later date if necessary. In this presentation, we haven't tried to list all of the 100+ tasks or so that we've developed, but we focused on a number of specific themes. Promotion, well, primarily advancing the required technology to build HVDC grids, has also taken a holistic approach to identifying the barriers and either providing solutions that may be applied or highlighting where work is still required. Over the last few weeks, many of my colleagues have presented conclusions on the videos that you may have watched earlier in this session and will continue to be able to watch after this session. Also, there are the various deliverables in Work Package 12. Understanding today's technical status requires evaluation of promotion and other R&D projects. We had to, first of all, what we tried to do is see where does promotion fit into the big picture. There have been a number of other EU projects performed, and what we did was evaluate where the gaps exist. That partially defined where the original promotion technology was or focus was decided, but also these projects continued during the process and during promotion, and we've used conclusions from the different projects to define a gap analysis. For each technology studied, we have therefore evaluated before and after promotion. I think Ian covered this partially in his presentation, and you see the gradual improvement in technology readiness level as each task within the promotion project was completed. If we then go forwards, we're looking at, we created a kind of technology gap analysis of what still has to be done to take promotion to the next step, or to take the technology to the next step and take the process forwards. What I'd like to reiterate here what Ian said. We see no longer any technical showstoppers for multi-terminal HVDC grids. We've looked at network protection, we've looked at network control, we've looked at circuit breakers and gas insulated switchgear as the focus of promotion. We've identified the technology research and selected this in the background, done desk research in the background. We've defined the requirements and specification of what is required. We've proceeded with technology qualification procedures. We've created the test environments required to take it a step further. And lastly, we've demonstrated where possible the technology available. That should take us to a sort of next step in terms of putting the technology that's been developed into an industrial situation where it can be tested in the real world. And also, it gives us the platform to standardize this equipment further. So in terms of the deployment plan itself, we've created a number of we've created the analysis into different paths. This we did for a reason. We had to steer the plan, and the technology path had its own path, and the economic and financing and non-technical path had its own path. But while we were researching, these paths took place in parallel, and to be able to sort of avoid problems of, well, you can't do this without this, we separated it out. So we created a path of creating the wind scenarios, the topologies, the technical choice, etc., independently of the non-technical trajectory, so that we assumed that the right environment was in place, or the technology was available for a legal construction, or vice versa. We also looked at the short term, because what we believe is that with the long lead times involved in constructing projects, we need to look at the short term period as well, and look at real projects and how these can be used to advance the technology going forwards. And with all this information, we pumped this into a deployment plan. So what I'm going to do, the first topic is advanced planning, and I will switch over to Olivier, who will go through this section.
Okay, thank you, John. As already said today, an important message is that there are no technical showstopper for building an HVDC grid. This allows us to ask the question, how do you plan an HVDC grid? Is there a single way to do it? How long in advance do you have to take action to make it happen? What level of coordination is required? To try to answer to this question, let's imagine what could be an HVDC grid by 2050. So in the promotion project, we made some scenarios to try to see what would be the development of the offshore grid by 2050. The image shown in the slides results from complex planning studies, and the bigger line show interconnection via the offshore grid. To answer to a question that was asked this morning, the interconnection capacities here are increased compared to the TYNDP forecast. When we compare with the grid shown in the video available on the promotion website, we can see some similarity. And it is to show that the vision of promotion at the start of the project is in line with the result of those complex planning studies. For example, the HVDC grid connects a high level of wind and all North Sea countries. John?
Yeah. Oh.
Okay. Yeah, that's fine. So we made some scenario, and we see we try to see what could be offshore grid by 2050. If we don't allow multi-terminal connection, then we will have a grid that looks like this, While in the next slide, if we see, if we allow multi-terminal, we have a more mesh structure. The mesh structure could be slightly different depending on the assumption we take. That is, that can be seen on the next slide. In the last option, we allow the offshore energy island, and we have another picture. All of this to say that probably none of this representation is an exact view of the future. There are still big uncertainties on technical, legal, and regulatory aspects. However, big steps forward have been done within the promotion project. And what you try to do is to explore several scenarios to try to cover realistic future. The two main dimensions that we consider was the concept that were already explained in Marc's presentation, and the wind scenarios. And we have in the wind scenarios, the low wind scenarios, where we have a target of 100 gigawatt by 2050, and the high wind scenario with a target of 205 gigawatt by 2050. So those representations can be used somehow to derive recommendation for deployment plan. And this next slide is very important. So an important message from our analysis is that the HVDC grid will grow incrementally. In the deployment plan deliverable 12.4, observations have been split for the period up to 2030, for the period from 2030 to 2040, and after 2040. In the background of the slide, you can see the wind target in the North Sea, which emphasize the real challenge and the fast growth that will be required in the offshore grid. So we believe in the first phase, we see an optimization of the current practices in the project that will be commissioned. So that will be mainly point-to-point connection with optimized design. We will also see potentially flagship project. It's important to note that this first phase is also key to set and coordinate all the building blocks for the next phase. Therefore, we don't have to wait 2030, and which is our estimated date for apparition of multi-terminal HVDC grid, to take action. We have to take action now in order to be able to build the most cost-economic grid by 2030 and so on. This could involve alignment of voltage level, for example, and all aspects that we call topological compatibility in the deployment plan. In the second phase, after 2030, there will be an acceleration of the offshore grid development to accommodate more than 120 gigawatts of wind by 2040. In that phase, everything has to be ready, technology, legally, and regulatory. We believe the multi-terminal HVDC grids will be built and potentially extended or interconnected to each other. In the last phase, we observed an increased interconnectivity of the grid, meaning that all North Sea countries will then be interconnected via the offshore grid. This leads to a few key messages in the next slide. First, preparation and consultation takes a long time. Therefore, we need to have an early planning. We need to take action early enough. Also, offshore investment are quite significant, and some form of anticipatory investment will be required in all our scenarios. The second message is that there is a strong link between maritime spatial planning and the development of optimum topologies. Therefore, a coordinated approach is recommended to select the best site for offshore wind, and that will lead to the development of the most cost-efficient grid. This coordinated approach could potentially lead to the need for reevaluating the possibility, reevaluating the allocation of already allocated zone in the sea. Therefore, we need coordination with also the decision maker. The fourth point is that offshore and onshore grid planning have to be done together. It is very important, and this might require adaptation in the planning tools and in the planning guidelines. Another point is that there are still some uncertainties in the years to come, but more clarity are expected and for example, via a practical experience on a short-term project. So indeed, planning the grid is very important, and we have outlined the need for planning ahead and increase coordination. But it is clear that the offshore grid has also to provide socio-economic benefits for all European citizens. This has also been studied, and I will go through some key points of this study. So basically, the four concepts developed within promotion actually allow the exploration of three axes. In the first one, we consider the removal of point-to-point connection to allow multi-terminal HVDC grid. In the second axis, we investigate increased cooperation and we relax some national constraints. On the last axis, we analyze the size of offshore hub, where we consider 2 gigawatts as somehow the size for offshore platform and up to 30 gigawatts for energy island. The cost benefits analysis has been split in a cost analysis, which was performed by estimating the number and size of each component needed to build the grid. And the benefit analysis has used KPIs related to socio-economic welfare, renewable energy sources integration, CO2 reduction, and security of supply. There were also some limitations in our approach, and unfortunately, we couldn't cover all possible dimensions. And aspects like power to gas, storage, and optimum onshore grid planning were not considered. However, we believe that those aspects could increase the benefits. As shown before, those are the four topologies that we use, and for each of these grids, we perform a cost-benefit analysis by simulating early dispatch from 2020 to 2050, and we did that based mainly on the TYNDP scenario. The main conclusion in terms of cost and benefits is that in terms of cost, the overall discounted capital and investment is lowest for the island solution, and this in spite of higher anticipatory investment. The cost of a meshed offshore grid is lower in terms of cable, but the overall cost could be similar depending on the cost for protection devices. We have to note that there is there are still some uncertainties on the cost, and that we have some degree of freedom also on the protection philosophy to reduce the cost. Overall, the mesh solution have higher benefit. We also did some sensitivity analysis, and all our sensitivity analysis shown increased benefits for the coordinated and meshed approach. So for example, if you have larger cables, then you will reduce significantly the amount of cables needed, and that will be mainly beneficial for the meshed solution. Also, the cable utilization rate is much higher in the coordinated concept because you can use the cables even if there is no wind. And that will lead us to my last slides, or where we saw that our objective analysis confirmed the benefits of a meshed offshore grid. In the first axis, we can say that point-to-point HVDC will still be used, but multi-terminal and meshed HVDC link show increased benefits and early in the timeline of the development. The large energy island has shown lower costs, and the hub concept is in all cases somehow also considered as meshed because it's connected to multiple landing points. It is worth mentioning that large-scale storage could be beneficial in all concepts, but also in the hub concept. In the final dimension, the European development has shown bigger and higher cable utilization rate. That could lead to potentially higher benefits. However, the wind scenario consider assume national targets, and we believe if we have European wind scenario, optimum European wind scenario, we will see even higher benefits of the European solution. And finally, before giving back the floor back to John, it has been observed that the benefits of the offshore HVDC grid in the North Sea are not limited to the North Sea countries, but can be beneficial for the whole Europe. So thank you for your attention, and John will now continue the presentation.
Thank you, Olivier. You've seen in the next section, you'll see the next issue is we need to solve market model issues. You've seen this previously in the select section by Marc, but many people perceive this as the key barrier in constructing meshed assets. And here I'd like to reiterate that also. Promotion has examined a new legal classification of hybrid assets and a market regulatory solution. In our primary research, Promotion concluded that this was required for market modeling only later as the grid became more complex. However, later on, we discovered that even simple grid structures, as illustrated here, it became clear that early on the small bidding zone model could also solve the legal constraint. Therefore, Promotion came to the conclusion, based on timing, that we should recommend both these solutions as we're unsure which is feasible earlier. However, as grid structures become more complex, our analysis, which evaluated the current zone structure, North Sea bidding zones and small zones model, the small zones model may consist of one or more hubs, but this has the highest social benefit for consumers. The North Sea bidding zone model had the least and therefore was abandoned, leaving us with these two solutions. The strengths and challenges of this are clear. The hybrid assets model is a kind of status quo solution. However, it goes against the current EU law. It also retains the current market models, which may be a benefit. However, this may not be suitable if the market becomes highly meshed. The small bidding zone model solves this market complexity, and our colleagues in Denmark believe that implementation is relatively possible. They already manage multiple bidding zones in Denmark. However, other countries involved in this may require both national legal and regulatory change at a national level, making broad implementation somewhat less straightforward for all North Sea countries, but we believe it may be worth the effort. I put in the next slide as well. Marc as well has covered funding and finance. The reason we've had a couple of presentations recently that suggest that it's not perceived as a value, as a real barrier, but I believe it should need consideration. Finance of the grid construction is anticipated to accelerate from 2030 to 2050. If a full grid is built as anticipated, the estimated investment is around 200 billion, and that's just for offshore. Onshore reinforcement is not included in those estimates, nor are the windmills. Potential for other infrastructure, such as power to gas, storage, may bring other costs and risks. Although funding is said to be available, we need to consider what kind of structure that will take in the future. Also, Olivier and others have mentioned anticipatory investment. Planning and cooperation between the owners, the regulator, and the operators of these assets is required and needs to be coordinated in order for those anticipatory investments to be made. Our analysis suggests, as Olivier said, that the long-term best solution requires certain anticipatory investments. If we cannot coordinate that, that best solution will not be achieved. And that brings a different investment profile into the equation that we're not used to. Then we have cooperation. There's been a lot of discussion about cooperation, and promotion itself is the result of the cooperation of many partners. And when I started this project, I said, well, who are the stakeholders? And this is a small selection. There's many more than on this graphic. The whole concept, each of these stakeholders has their own meaning on various aspects of what's going on and needs consultation. You can put in to each task that we've created as many of these people or as few as you require. So we've tried to limit the people who can impact a decision in the tasks we've defined, but in those tasks you have to be, those people will have to be aware of the additional stakeholders. So in terms of the specifically the HVDC environment, we had 7 recommendations. You require political agreement, you require regulatory compatibility, project alignment, system compatibility, function compatibility, vendor interoperability, and contractual compatibility. So we need to adopt a common vision of the North Sea energy resource. We need to align on multinational power systems rules of engagement. We need to coordinate power system planning regionally and comprehensively. I believe Kees said also earlier that around the North Sea there are European countries, but there are also a few non-European countries that also need to play a role in this system. We need to agree on compatible electrical ratings for HVDC equipment. We need to agree on common functional requirements for HVDC for the different vendors of HVDC equipment. We need to align procurement best practices with a kind of new HVDC paradigm. In the past, nearly all the HVDC projects have been point-to-point. If we start to mesh, we have a new relationship between different vendors' equipment, between how we acquire that equipment and how we put it together. This has quite a large impact at all stakeholder levels. If we talk about the instruments we've discussed, there's multilateral treaties, regional or North Sea Treaty, the North Sea Energy Cooperation, TYNDP processes, the Memorandum of Understanding, system operational guidelines, grid codes, standards, recommended practices. All these need to be organized. The different stakeholders here, they look as if they're aligned, but many of these stakeholders have an influence on different instruments and different levels. And then, as I say, there's also stakeholders outside this list that also feed into the coordination role. The deployment plan has tried to put these in a row, and here you see the timeline we do have in the document who we believe the stakeholders are and who should participate in the process. But we've taken out a number of the tasks, split again into technology, the markets, legal and regulatory, and governmental. What you see on this slide is that much of the work has to be done in and possibly completed in the first 10 years, if not eventually the first 15 years from 2020 to 2035. So one of the things that we also came to decide on is that you have to start today with a real project. Within promotion, we looked at a number of short-term projects at the construction of a full-size demonstrator, which is perceived as too expensive. We have costed it out, and we came to something like 8 billion, which I think is probably too expensive for most people. So we looked at what was in the current TYNDP, or the current TYNDP at the time, and we looked at the planned existing HVDC links, and then we identified potential locations where it was either being implemented or was implemented. Eventually, we managed to persuade at least 3 owners of projects to agree to support them in pre-feasibility studies. We made different studies depending on the needs or what we were able to do for the different partners, and we looked at the Southwest Link and Hansa Power Bridge link. We looked at the wind connector between the Netherlands and the UK, and we looked at Bornholm Island, the Clean Stream project, and we did studies on these. What we are convinced of is that we need to look at a number of pilot projects and how these build up to be able to address the complexity once a DC grid becomes more complex and more difficult to handle. There are ideally a number of projects of varying complexity that are identified on this graphic, and again, this graphic, as you go across, indicates an increasing level of complexity. So as conclusions for the deployment plan, we believe that the technology is ready for multi-terminal HVDC grid development. It has, at the moment, still some work to do. There's further standardization work needed on multi-vendor HVDC grid integration, on functional compatibility, procurement and contractual compatibility, and on multi-vendor interoperability. And I think this slide I made yesterday or the day before or even a week before, yes, it confirms the results of polls taken today. International collaboration and coordination is absolutely key to establish the regulatory and legal compatibility. If I think about that, I have to think back to Tuesday of last week when TenneT presented its offshore vision, and 3 government departments indicated, at least at a certain level, a level of political agreement and common goal. And that is the kind of that now has to filter down into the operational world where things now happen. We need project and planning compatibility, and there I think there is still quite a way to go. And we need a kind of a topological compatibility where we have common goals. A full-scale project, pilot project, is the best way to demonstrate the feasibility of HVDC grids and to realize the benefits available. I'd like to thank you for your attention. I'd like to thank, actually, I don't have a slide with pictures of all the people who participated in this, but there were 16 partners in my work package. There are 34 partners overall, and I believe that all parties had influence on our results. So thank you.
Thank you, John, for an interesting presentation. And I hope that our audience of strong offshore development believers and some mild HVDC enthusiasm have enjoyed our presentations on what technology is available, and that you agree with us that the technology is mature, but that there remains a lot of work to be done in the integration of it, and most notably through interoperability, and that this is best shown by a pilot project. Furthermore, the overview of legal, regulatory, and economic solutions that we have worked on, and the key conclusion that really we need to start now with implementing those. That something must be done about hybrid assets to enable them, but that there is a split between whether this should be done through market design or the more conventional approach for asset classification. And most of us actually agree that both could be reasonable options. The regulatory and market setup is key in this, but governance and political support is required. And if that is in place, we believe that financing will follow, and that ownership is actually not very important to consider in all of this. Well, after lunch, we hear from a select panel of industrial leaders about how they see the solutions for these kind of problems and aspects that still need to be solved. So please come back here in 20 minutes, and we will continue with the panel presentation. Thank you for your attention so far.